Hello, everyone. Thanks for the introduction. Today, I'm going to present our work, AirExpress, enabling seamless in-band wireless multi-hop transmission. This is a joint work with my lab mates Bo Chen, Ouyang Zhang, and my advisor, Kannan Srinivasan. In this work, we enabled the cut-through in wireless. Before I propose our system, let's first have a quick recap of what is cut-through in wired network. In wired network, cut-through is a kind of routing in which every router forwards the received signal with little or even no decoding. Therefore, a packet can be transmitted seamlessly along the path. The reason that we can enable cut-through in wired network is that signals are transmitted via different wires. Therefore, they are not interfering with each other. So all the nodes along the path can transmit and receive at the same time. But in wireless, things are different, as wireless transmissions are done in a broadcast fashion. Therefore, if one node is transmitting, all the other nodes need to be silent at the same time. Therefore, look at this figure. The destination can only receive one packet every 4 time slot in this 4-hop link. So we are wondering, what if we can enable cut-through in such a system? Then the destination can receive one packet every one time slot. So inspired by the increased throughput and decreased latency, we developed and implemented AirExpress, which is the first fully functional cut-through system in wireless. So let's see how we achieve this by looking at the challenges we face when building such a system. The most fundamental challenge in building such a system is various types of interference. Assume the source is transmitting. All the 3 routers are amplifying and forwarding the received signal. Then how many types of interference each router would see? Let's focus on B. The first interference is the self-interference, because router B needs to transmit and receive at the same time. Beyond self-interference, router C's forwarding introduces what we call forwarder interference to router B. And the third type of interference is called cross-hop interference. Here in this figure, the source, which is 2 hops away from B, its transmission causes cross-hop interference to router B. So if we want to enable simultaneous transmissions in this link, we need to deal with all the 3 types of interference. And among the 3 types of interference, the self-interference is easy to handle because we have full duplex technique. But what about the other 2? One naive solution is to mirror each of the interfering channel and cancel each of the interference sequentially. However, this solution is not practical and is very inefficient. The reason is that there are so many interfering channels in this link, and the number of interfering channels increases as the number of hops increases. So instead, in AirExpress, we propose a channel estimation scheme in which every router or every forwarder only needs to do channel estimation once upon a link build. That sounds amazing. Let's see how we achieve this. First is the forwarder interference. Assume B receives signal from A, which is X of t. Then the self-interference is the output of the self-channel, which is indicated by the red line. And the forwarder interference is the output of the forwarding channel, which is indicated by the green line. You can see it's very interesting that the self-interference is similar to forwarder interference. The only difference is that the self-interference travels in the air, but the forwarder interference travels not in the air, but also through another node C. Therefore, the timing of self-interference and the forwarder interference is different. So this figure shows the timing we got during an experiment. The first jump of the received signal strength is caused by the arrival of self-interference, and the second jump is caused by the arrival of forward interference. In a full duplex radio, we only have self-interference, so we only need to mirror a self-channel. But here, forwarder interference is superposed with the self-interference. Then what we should do? Of course, you can mirror the self-channel and the forwarding channel separately and cancel them one by one. But it looks more efficient if we view the superpose the self-interference and the forwarding interference as the output of one superposed channel. However, wait a minute. Can we mirror the superposed channel? Because the superposed channel contains the forwarding channel. And as I mentioned, the forwarding interference travels not only in the air, but also through another node. And as we know, two radios always have frequency offset. So if the forwarding channel contains frequency offset, then the superposed channel is changing over time. That means the channel estimation we got during training will not be accurate at all when we do cancellation. So let's take a step back and look at the forwarding channel more closely. Assume node B works at frequency omega B. Node C works at frequency omega C. When B sends out the signal x of t, C's processing introduces a frequency offset omega B minus omega C. But when C sends out the received signal, then B's processing introduces an opposite frequency offset, which is omega C minus omega B. So in the received signal at B, it contains no frequency offset. That means the forwarding channel is frequency offset free, and we can mirror the superposed channel as one single channel and do the cancellation. So far, we have achieved the ideal causal system if we assume each node's transmission only affects its adjacent nodes. But our system, AirExpress, achieves more than that. We also successfully dealt with the cross-hop interference. Cross-hop interference is very challenging because there are many cross-hop channels in the network. Here is an example. In this 4-hop link, D causes cross-hop interference to B. This cross-hop channel looks simple at this moment. But if you look at it more carefully, you will see there are many traces that could possibly contribute to that channel. Because of space limit, we list only 3 of them here. The first one is from B to D. The second one is from B to C to D. And the third one is from A to C to D. And among all the cross-hop interference, not all of them can be canceled. The reason is that some of the cross-hop interference are causal, but some are not. For example, in these 3 traces, the first 2 are causal, but the third one is non-causal. The causal cross-hop interference are just like the forwarder interference. The difference is that the causal cross-hop interference travels through multiple nodes, but forwarder interference travels through only one node. So, based on the same logic, as I discussed in the forwarder interference cancellation part, we can view the superposed channel which contains all the causal traces, including the self-interference, forward interference, and the causal cross-hop interference as one channel. If we can mirror that channel, we can cancel all the causal traces altogether. For the non-causal one, our design philosophy is to leave them there. The reason we can do that is that in cut-through routing, the source is the only signal generator. So all the non-causal traces originate from the source. Therefore, they can be viewed as multipass components of the intended signal. And many radios have designs to deal with multipass, so it is safe to leave them there. Now the problem is how to cancel the causal ones, or how to get the estimation of the superposed causal channel. We propose a hierarchical cancellation structure. Using this structure, each node only needs to do channel estimation once to get the causal channel. The idea of this structure is to enable the forwarder one by one in the direction from the destination to the source. Here is a detailed process. First, D is enabled. When D sends out training sequence, because D has no descendant forwarder, it actually performs self-channel estimation. After that, D switches to forwarding mode, and C is enabled. And when C is enabled, C sends out a training sequence. And at this time, D is active. So C gets the estimation of the superposed self-channel and forwarding channel. And then B is turned on. B's training helps B get the estimation of the self-channel, forwarding channel, and the causal cross-hop channel. In this way, AirExpress link or cut-through link is built, and each of the forwarder only does channel estimation once. So far, we have successfully dealt with various types of interference in the network. And that means we can enable simultaneous transmission in the network. But to enable cut-through, there are still many other challenges. The first one is noise accumulation. Because in our design, the forwarder simply amplifies and forwards the received signal with no decoding. Therefore, the noise might accumulate infinitely along the path. Then the accumulated noise would deteriorate the SNR at the destination. To solve this problem, we propose a design called virtual hop. The idea is simple, just to divide the long path into smaller hops, and we call these smaller hops as virtual hops. Here is a simple example. We divide this 5-hop link into 2 parts. The first one is a virtual hop contains 3 hops. The second one is a virtual hop contains 2 hops. And the joint forwarder performs decode and forward instead of amplify and forward. So the noise would not accumulate infinitely along the path. We propose virtual hop also for other considerations, like bottleneck link and latency considerations. Because of time limit, I won't discuss the details here, but I highly encourage you to read our paper. Another challenge of enabling cut-through in wireless lies in the MAC layer. As traditional carrier sensing only detects transmissions in a single collision domain. But AirExpress requires carrier sensing extends beyond a single collision domain. So we developed and implemented a MAC and routing algorithm. By using that algorithm, AirExpress nodes can be deployed in a distributed way. And again, details are in the paper. You can read it if you are interested. So far, I have finished the design part. Now let's look at the implementation. We implemented AirExpress on a software-defined radio platform, which is NI-PIXI 1082. All the AirExpress nodes work at 2.4 GHz with 20 MHz bandwidth. Each of the nodes is equipped with a unified cancellation block, just as I described before. And we evaluated AirExpress performance in an indoor setting with 20 locations to place these nodes, just as this picture shows. During each measurement, one source and destination pair was randomly selected, and the traces that maximize their TDMA performance are used to build an AirExpress virtual hop link. So this figure shows the AirExpress throughput gain over TDMA. The first thing we can see is that as the virtual hop size increases, the throughput gain increases. One thing we should know that the upper bound of the throughput gain is given by the virtual hop size. For example, in a 4-hop virtual hop link, the throughput gain upper bound is 2. And we can see that in the high SNR region, the gains just approach the upper bounds as we expected. But in the low SNR region, AirExpress has a similar performance as TDMA. The reason of this phenomenon is that the noise accumulation would deteriorate the SNR in the low SNR region more severely. So from this figure, we can see that AirExpress virtual hop link works well, and it implies our hierarchical cancellation structure works nicely. Through the experiment, we have validated the AirExpress performance in a single flow network. But we are also curious about its performance in a large network where multiple flows exist. As radios are expensive, we cannot evaluate that performance in real testbed, so we ran a simulation in NS3 with 100 nodes randomly placed in a 1,000 meter times 1,000 meter area, and multiple flows are generated. Again, we compare AirExpress with TDMA, and we also vary the virtual hop size from 2 to 5. We fed the residual interference information to the simulation, which is measured from real testbed. This figure shows the throughput performance of AirExpress and the TDMA. Here, this is the red line is the 4-hop AirExpress. 4-hop AirExpress means the maximum virtual hop size in that network is limited to 4. So the upper bound of throughput gain is 4. And from the simulation, we see that 4-hop AirExpress outperforms TDMA by 2 times on average. And the delay performance is given in this figure. On average, TDMA has a 3 times delay over 4-hop AirExpress. When we vary the virtual hop size, we got this figure. The first thing we should notice is that when the virtual hop size increases from 2 to 4, the throughput increases. But when the virtual hop size is larger than 4, the throughput stopped increasing. The reason of this is that in a 5-hop link, the noise accumulation has deteriorated the SNR. Therefore, the throughput stopped increasing. This figure tells us that virtual hop design is essential. Otherwise, the noise would accumulate infinitely along the path and hurt our throughput gain. In conclusion, we built AirExpress, which is the first fully functional in-band wireless cut-through system. And AirExpress challenges the traditional description of transmission patterns in wireless ad hoc network. And we are hoping that AirExpress can be a building block of future multi-hop network architecture. Thanks for listening, and I'm glad to take any questions.